Today we are going to learn about understanding p-values and hypothesis testing. This video will teach you how to calculate and interpret p-values to validate the results of your machine learning models.
Welcome to our video on understanding p-values and hypothesis testing. In the world of statistics and machine learning, p-values play a crucial role in hypothesis testing, helping us determine the statistical significance of our model results. Today, we'll explore what p-values are, how they are calculated, and how they can be interpreted to assess the accuracy and reliability of model predictions. By the end of this video, you'll be equipped with the necessary skills to calculate and interpret p-values, enhancing your ability to validate the results of your machine learning models.
P-values are a fundamental concept in hypothesis testing, which is a method used to make statistical decisions using experimental data. The p-value quantifies the evidence against a null hypothesis. Specifically, it represents the probability of observing results at least as extreme as the ones obtained, assuming that the null hypothesis is true. In hypothesis testing, you start with a null hypothesis, which is a statement of no effect or no difference, and an alternative hypothesis, which is what you want to prove. The p-value helps you determine whether to reject the null hypothesis in favor of the alternative. A low p-value indicates strong evidence against the null hypothesis, suggesting that you should reject it, while a high p-value suggests there is weak evidence against the null hypothesis, so you fail to reject it. The threshold for determining what is considered low is called the significance level, often denoted as alpha. Common practice sets this threshold at 0.05, meaning there is a 5% risk of concluding that a difference exists when there is none. Understanding p-values is crucial in research as it helps quantify the evidence and supports decision-making.
Now that we understand what p-values are, let's dive into how we calculate them. The calculation of p-values depends on the statistical test being used and the nature of the data. Common tests that yield p-values include the t-test, chi-square test, and ANOVA, among others. To calculate a p-value, you first need to determine the test statistic, which varies depending on the test. For instance, in a t-test, the test statistic is the t-score, calculated from the sample data. Once you have the test statistic, you compare it against a statistical distribution, such as the normal distribution for z-scores, or the t-distribution for t-scores, to find the probability of observing a statistic as extreme as, or more extreme than, the observed value. This probability is the p-value. It's crucial to ensure that the assumptions of the statistical test are met before calculating the p-value. For example, the t-test assumes that data is normally distributed and that samples have equal variances. Failure to meet these assumptions can lead to an incorrect p-value. Let's illustrate this with a practical example. Suppose we have two sets of data representing test scores from two different teaching methods. We can use a t-test to determine if there's a significant difference between the two methods. We calculate the t-score and then determine the p-value to assess the significance of the results.
Interpreting p-values in the context of machine learning is critical for validating model performance. In machine learning, p-values help assess whether the results of a model are statistically significant or likely due to random chance. For instance, when comparing the performance of two models, a p-value can indicate whether the observed difference in accuracy is statistically significant. However, it's important to distinguish between statistical significance and practical significance. A statistically significant result might not always translate into meaningful or practical improvements in a real-world context. P-values offer a quantitative measure of evidence but do not speak to the size of an effect or its practical implications. Furthermore, while p-values are useful, they have limitations in the machine learning context. For example, with very large datasets, even tiny differences can appear statistically significant. This calls for a careful interpretation of p-values alongside other metrics like effect size and confidence intervals. Despite their limitations, p-values provide valuable insights into model validation, helping practitioners make informed decisions about model performance and improvements.
P-values are often misunderstood and misused, leading to several common misconceptions. One frequent misunderstanding is that a low p-value confirms the truth of the alternative hypothesis. In reality, a p-value simply measures the strength of evidence against the null hypothesis, not the probability that the null hypothesis is true. Another misconception is equating the p-value with the size of an effect. A significant p-value doesn't necessarily imply a large or important effect, it only suggests that the observed effect is unlikely under the null hypothesis. Confusion also arises between p-values and type 1 and 2 errors. A type I error occurs when a true null hypothesis is incorrectly rejected, while a type 2 error occurs when a false null hypothesis is not rejected. The p-value is related to the probability of a type I error, but it doesn't provide information about type 2 errors. Additionally, in large samples, even trivial differences can yield significant p-values, leading to misinterpretation of results. Finally, over-reliance on p-values can hinder scientific inquiry. It's crucial to consider other statistical measures, theoretical justifications, and the broader context of the research. Understanding these misconceptions helps in the correct interpretation and application of p-values in hypothesis testing. Choosing the right significance level, often denoted by alpha, is a crucial decision in hypothesis testing. The significance level represents the probability of making a type I error, which is rejecting a true null hypothesis. Common choices for alpha are 0.05, 0.01, and 0.10, with 0.05 being the most widely used. The choice of significance level involves balancing the risk of type I and type II errors. A lower alpha reduces the likelihood of a type I error but increases the risk of a type II error, which is failing to reject a false null hypothesis. The selection of alpha should be guided by the context of the research and the consequences of potential errors. In some fields, such as medicine, stricter significance levels like 0.01 are favored to minimize the risk of false positives. Conversely, in exploratory research, a higher alpha might be acceptable. The chosen significance level also impacts decision-making in hypothesis testing. It determines the critical value against which the test statistic is compared, influencing whether the null hypothesis is rejected. Therefore, selecting an appropriate significance level is a vital part of the hypothesis testing process, requiring careful consideration of the research context and objectives.
P-values play a significant role in validating model improvements in machine learning. When developing models, it's essential to assess whether changes to the model, like using new features or algorithms, lead to significant performance improvements. By comparing the performance metrics of the original and updated models, and calculating the corresponding p-value, you can determine the statistical significance of the observed differences. This statistical validation helps ensure that improvements are not due to random chance. However, while p-values provide evidence of statistical significance, they should be interpreted alongside practical considerations. For instance, a statistically significant improvement might not be practically meaningful if the effect size is small. Real-world validation involves considering how these improvements translate into the actual application context. Continuous model evaluation is also vital, as models can degrade over time due to changes in data distribution. Regularly assessing model performance with p-values aids in maintaining model reliability and accuracy. Ultimately, p-values are a valuable tool in the model validation process, helping practitioners make data-driven decisions about model improvements. Let's explore some practical examples of how p-values are used in machine learning applications. One common application is in comparing the performance of different algorithms. For instance, suppose you have developed two classification algorithms and want to determine which one performs better. By comparing their accuracy or precision recall metrics using a statistical test, you can calculate the p-value to assess if the observed difference is statistically significant. Another application is feature selection, where p-values help identify which features contribute significantly to the model. By calculating p-values for each feature, you can determine which ones to retain in the model. P-values are also extensively used in A/B testing, where they help assess the effectiveness of different versions of a product or feature. In predictive model validation, p-values help test the hypothesis that a model's predictions are better than random chance. These practical examples demonstrate the versatility of p-values in various machine learning contexts, aiding in data-driven decision-making and model optimization. Python offers several powerful libraries for calculating p-values, facilitating statistical analysis in machine learning. One of the most popular libraries is SciPy, which provides a wide range of statistical functions, including those for hypothesis testing. The scipy.stats module includes functions like test_, and for t-tests, and chi2_ contingency for chi-square tests, making it easy to compute p-values. For more advanced analysis, the stats models library is a valuable tool. It offers comprehensive statistical models and tests, providing detailed results, including p-values. Stats models integrates well with other Python libraries and machine learning frameworks, making it a versatile choice for statistical analysis. To illustrate, let's consider a hands-on example. Suppose you have a dataset with two groups and want to compare their means. Using SciPy, you can perform a t-test with just a few lines of code. From SciPy import stats, t_stat, p_val equals stats.test_ in group 1, group 2. This simple example demonstrates the powerful capabilities of Python libraries in calculating p-values, supporting robust statistical analysis in machine learning applications. In conclusion, understanding p-values is essential for effective hypothesis testing and model validation in machine learning. Throughout this video, we've explored what p-values are, how they are calculated, and their interpretation in various contexts. We've also discussed common misconceptions, the importance of choosing appropriate significance levels, and practical applications in model validation. By leveraging tools and libraries in Python, you can efficiently calculate p-values and enhance your statistical analysis capabilities. We encourage you to delve deeper into this topic and apply your newfound knowledge to real-world machine learning challenges. Thank you for joining us on this educational journey, and we hope you found it valuable and insightful.